Algebra 1 students, welcome to your 7.6 notes. Exponential functions is what we'll be looking at today. We've spent a lot of time this year graphing, but it's primarily been lines, and we're going to start looking at some other shapes as we move through the course, and today is one of those days, exponential functions. So an exponential function is a function in the form y equals a times b to the x power, where a can't be 0, b has to be positive, and also can't equal 1. If the b value were 1, you wouldn't have any change, because 1 to any power is 1. So in any case, and then also x is a real number. Okay, thanks for that. So let's take a look. I've given you 4 graphs here. On the left, you have y equals 2 to the x, and then the reflection of that graph, y equals negative 2 to the x. So we're just reflecting across the x-axis. You can see how that graph is, we're moving to the left. It actually looks like it's at 0, but if you were to investigate that more closely, you would find that it's actually approaching 0 as you move to the left, but it's never going to actually get there. And then as you move right, especially once you pass x values of 0, this starts to climb, well, exponentially. That's where that word comes from. So, and in the same by the same token, the negative 2 to the x has that same growth. It's just, in this case, it's actually moving downward. Now to the right, you can see what happens when our value, which is our b value here, is actually a number between 0 and 1. Instead of having growth, where the graph moves upward, we have decay, where it moves downward and approaches 0. So these graphs are really similar, all 4 of them. They're basically just flipped opposite directions, and we'll look more closely at how we come up with some of those in just a moment. All right, so let's take a look at what does it mean when we talk about exponential? What does it mean when we talk about linear? So let's start with the first one. Is this exponential or linear? Now what I'm looking at, first of all, I see how my x values are consistent. 0, 1, 2, 3. I've got change, it's constant. Then I look at y values and I say, okay, I'm going from 5 to 8, 8 to 11, 11 to 14. And the question becomes, what am I doing to make that happen? Well, each time I'm adding 3. And when you see something like that, where you're adding the same amount each time, that's a linear relationship. We would say that we have a common difference of 3. I know it didn't ask that in the instructions, but I think it's good to think about that. Common difference of 3. All right, the second one. Again, the x values have constant change, 0, 1, 2, 3. Pretty simple values. But take a look at these numbers. Negative 2 to negative 4. Negative 4 to negative 8, and then negative 8 to negative 16. It's not constant change by adding or subtracting, but what it is, it's constant that we're multiplying by 2. Every single step is multiplied. So this is exponential. We're multiplying by the same number each time. And then our ratio is 2. So it's effectively what we're saying is when a relationship is linear, you have a constant difference. You can add or subtract the same number. When it's exponential, you have a constant ratio. You're multiplying, or you could think of it as dividing at times, by the same amount each step. All right, why don't you guys pause the video, try figuring out number 3 on your own, then compare your answer to mine. All right, welcome back. You can see my work here when I scroll down for you. What I found on number 3 was that every step I was multiplying by 1/2. Now you may have thought, well, wait a minute, that's dividing by 2, isn't it? Yeah, that's true, it's dividing by 2, but we want to think in terms of multiplication when we find an r value. And so I said this is exponential growth. Actually, it's decay. It's exponential. We'll talk about that another day. But the r value here is 1/2. Again, I went a little beyond the instructions because here it just said, is it linear or exponential? But I thought it would be good, since we knew it was exponential, to go ahead and have a quick discussion about the r value. There it is. We're moving on. All right, suppose 30 flower beetles are left undisturbed in a warehouse bin. Sounds good. The population doubles each week. The function f of x equals 30 times 2 to the x gives the population after x weeks. Now this x weeks is important. How many beetles will there be after 56 days? The reason I underline those two things is because you have to consider 56 days is equal to exactly 8 weeks. Make sure you don't plug in 56, your number, or you would be treating it as if it were 56 weeks. So what we're doing is f of 8, that means after 8 weeks, what's this function going to be? In this case, the function represents the population. And so f of x equals 30 times 2 to the 8th power. Now my guess is most of you, and including me, would want to use a calculator at this point. 2 to the 8th is what you would probably want to do first. 2 to the 8th is 256. And then if you multiply that by 30, you'd get 7,680. So you would know then that the population of flower beetles would be 7,680 after 56 days. You could write that as 8 weeks if you preferred, but I'm good with 56 days. All right, so there's our solution right there. So let's do a little graphing. So we saw a couple graphs on the first slide just to give an idea of what these would look like. But we're going to go ahead and do one of these by hand. And now what we want to actually do is a little t-chart here. So we're going to do x, and then over here we'll have a y. But I'm going to go ahead and put the work in between. So this is 2 times 3 to the x, which is how we'd get our y value. So we have to choose good values for x. Any number would actually work. It's really important with exponential graphs that you consider like negative values and positive values so you can kind of get an idea of what the data is going to look like. So my graph is going to be with input values of -2, -1, 0, 1, and 2. So what I'm doing now is I'm plugging in -2, -1, 0, 1, and finally 2 into this so I can see where the y values are going to come from. So let's do this. 3 to the -2 is where I would start. Remember, when you do a negative exponent, you have to flip the fraction. So this is basically 1/3 squared, so that's 1/9, and 2 times that would be 2/9. 3 to the -1 is 1/3 times 2 would give me 2/3. 3 to the 0 is 1 times 2 is 2. 3 to the first times 2 is 6, and 3 to the second times 2 is 18. Now I'm going to plot these points, -2 and 2/9. I know 2/9 is kind of a weird one to try to graph. It's okay, we're just doing a little bit of an estimate. -2 and 2/3, maybe it should be in between a half and a whole, somewhere about there. 0, 2, I can get that one pretty accurate. 1 and 6 would be up here. Once I hit 2 and 18, I'm off the grid, so I'm going to go ahead and just stop right there and then draw my sketch. Now what we have going is if we were to move further and further to the left, we would see that this graph is going to approach but not actually cross or touch 0. So even though it looks like it's basically right on 0 out here, it's just getting really close without touching it. And if you actually put this graph on Desmos and zoomed in and just kept moving to the left, you could examine that with a little bit more detail and actually see what's going on. We'll get to Desmos later, but for now I want to make sure you know how to graph by hand, and that's our focus. Now, by the way, when you have this situation where a graph approaches a line but doesn't touch it or cross it, we call that an asymptote. I'll spell that. So asymptote, A-S-Y-M-P-T-O-T-E. So this is right here a horizontal asymptote. It's the x-axis, but in this case it serves as an asymptote. All right, so we're going to do another graph here. This one, notice that we have a fractional value inside the parentheses, which means that the exponent is applying to a number less than 1. And that's going to make a difference on the direction our graph moves. But we're just going to plug numbers in and see how this works. And again, I think good values to use would be the ones that we used on the last, -2, -1, 0, 1, and 2. So if I'm finding the first value, if my input's -2, I'm going to have 8 times 1/2 to the -2 power. That's 8 times 4, which would be 32. Why don't you guys pause the video, fill out the rest of this chart, and then we'll graph it together. Pause it. Stop the video. All right, welcome back. If your points don't agree with mine, figure out who's right between us. I think it's me, but I've been wrong before. All right, so I'm going to start graphing here. You notice the first 2 points, -2 and 32, -1 and 16, those are way off the screen. So I'm actually going to start with 0 and 8, and then 1 and 4, 2 and 2. Now, this is not the greatest number of points for our graph. In this case, it's kind of hard to tell what's happening, in my opinion. So I would think about this, and I wouldn't do a whole lot of work to make this happen, but imagine if you went a couple more steps, like a 3 and a 4, and look at the pattern here. You notice we have that common ratio where you're multiplying by 1/2. Well, that's kind of interesting. That's the number right there, isn't it? Okay, so we're multiplying by 1/2, or you could think of it as dividing by 2. So I know I'm going to go to 1 and then 1/2, and if you wanted to go further, you could. But this will give me a lot better view of the way this graph is bending, so to speak. And it's just getting closer and closer to 0. But again, no matter how far out there you go, you would find that you would never actually get to 0. You would just approach. Again, we have that horizontal asymptote. All right, these are a little tough to draw on my board, but that is phenomenal if I grade to a curve. All right, so there's the general shape of the curve. Again, I'm looking for general shape. I'm looking for the correct y-intercept. Things are facing the right direction. I'm not going to go in and say, at -0.3, you should have been here. I'm just looking at big picture stuff. All right, so the last topic we're going to talk about is solving by graphing. We're going to go back to your old friend Desmos. Now, I actually like these problems a lot. They're pretty simple to solve, but it's not quite as basic as when we solve linear equations or linear systems. But we're going to treat this like it's a system, essentially, and I'm going to have the left-hand side be my first equation, 4 to the x. That's really y equals 4 to the x. And then my second is going to be 3x plus 4. So if I graph those two things, then I need to look and see, okay, well, where do they meet? Where is the intersection? And I've got two intersections that you can see right there. By the way, this one to the left, make sure you don't click this axis. That's not an intersection, that's an x-intercept. This one is the one you want, where they actually intersect each other. And so we have two answers here. Now, note that it's not really an ordered pair situation, even though we see that on the graph. What are we solving for when we solve this equation? Well, we're solving for x. So I'm going to put the two values for x. So I'm just going to call it 1.56 and then -1.28. Those are my two values. All right, I'm going to slide this over so we can see our next one here. Here's our last problem, number 8. We're going to treat these in real similar ways to what we did 7. So I'm going to put on one side -2x plus 3. It's just in line with a slope of -2. And then we have our exponential graph, 3 raised to the x power. Now you'll note this time that there's only one intersection. It's that point right there. So we would just say x equals 0. And I'm okay with like nearest hundredth, 0.57. But again, those two values are just coming straight off of the graph. And it's only x values. We don't have to worry about y values here. All right, folks, you have a spectacular day. Make sure you come to class ready to work, have those notes filled out, and we will be ready to roll. Have a great day.